everyone. I'm going to talk about a section from the irrigation scheduling manual that's going to focus on the theory and application of soil-based irrigation scheduling. So I wanted to do a quick overview. I wasn't quite sure what was going to be covered in the other presentations, but here's a really brief review of the key definitions and concepts of soil moisture that are going to really set the groundwork for when you're doing the soil-based irrigation scheduling. So we've heard it a few times, I guess, but I'll say it again. So soil texture is going to affect soil water, and that's really just due to differences in porosity between a coarse and a fine textured soil. So if you can see from my graph, there's generally going to be less available water in a sandy soil compared to the clay soil, and that's going to impact the water requirements for irrigation scheduling. So I don't think I can figure out how to use the pointer, but to your left, that's the sandy loam soil over there, and then the clay's over here on the right. So you can just see that that change between the field capacity and permanent wilting point. And permanent wilting point is, plant available water is that point between field capacity and permanent wilting point, and that's obviously going to change with the texture. And at permanent wilting point, that's where you're going to see those negative impacts to yield. So irrigation schedules are designed to maintain that soil moisture in the safe zone, which is between field capacity and the maximum allowed depletion, which is usually set at about 50% of plant available water. So irrigation is going to be triggered at that maximum allowed depletion, and then you're going to irrigate or calculate the depth of irrigation to bring the soil back up to field capacity. And rooting depth is another important consideration when you're scheduling irrigation, because that active root depth and root zone is obviously going to change throughout the field season as the plant develops. And that just translates into the need to also kind of increase that depth of soil that you're going to be managing throughout the field season as well, just to make sure that there's enough water to actually wet the entire root zone when you have that irrigation application. And we mentioned this before too, but it's really important to focus on that top 50% of the active root zone. That's where the crop's going to draw the majority of its water from. So, whether you're collecting samples or inserting a probe, it's really important to make sure that you have that collection point down to, say in canola, which is a meter active root zone, you want to at least be monitoring down to 50 centimeters. And soil-based scheduling is just one of 3 approaches that you can use. Evan already went through weather-based and plant-based. But this method is exactly what it sounds like. All we're doing is monitoring the soil moisture and then determining the irrigation requirements, which are going to be the timing and the depth of application. And another important point to, make sure of is that you're collecting that data or inserting that probe at a representative point in the field. Whether, in an ideal situation, you're collecting that soil moisture data from multiple locations and multiple depths throughout the field. But it's also important to, if you're just going to take it from one collection point, that it is representative so you're not over or under watering. And so soil moisture can be directly measured or else indirectly estimated using a variety of different methods or probes. So that's what I'm going to spend the rest of this presentation is just going through some of the different technologies and methods available for the soil-based irrigation scheduling. So the gravimetric method, this is an extremely reliable method because it is actually a direct measurement of the water in your soil. However, it's very intensive and it requires the person to go out there, obviously collect your soil, different locations and different depths, and then of course dry it in the oven for 12 to 16 hours, and then complete the necessary calculations to get volumetric water content and then eventually irrigation depth for application. So that's why it's really, due to that intensive nature, it's really more practical as a periodic check. I don't think anybody probably should or could schedule their irrigation this way, but for some of the other sensors that we're using, it's a really good way to go out there and confirm that yes, you are measuring the soil accurately, and to kind of just calibrate some of those other methods. So the pros, it's very inexpensive and accurate. However, there's that trade-off with the time that you need to go out. Also, having an industrial drying oven on hand is maybe also a barrier to this method. And then next up is the hand feel method. So Kara already did a wonderful job of describing this, but very briefly, the hand feel method allows you to estimate soil moisture just by directly handling or manipulating the soil in your hand. And after collecting samples through the rooting zone and estimating your plant available water, you need to calculate the required irrigation depth to bring that soil back up to field capacity. Similar to gravimetric method, same pros and cons almost. It's inexpensive. However, it's maybe not accurate. So this just, I guess, depends on the experience of the user that actually is completing the method. So there is a potential if you don't have the experience, you're not maybe going to get the right moisture content from this method. So now I'm going to move on to some of the sensors that are available. I've never actually used a tensiometer before, but I'll just grab it here. So this instrument actually measures the soil suction or the soil tension, I guess. And then that tension can be translated into moisture content based on the texture. Okay. So the tensiometer itself is a solid tube. It's sealed at the top with this ceramic, not ceramic, it's a plastic cup, there we go. And then there's the ceramic tip here at the base. So the tube is filled with water, it's inserted into the soil, and then this porous ceramic tip allows the water to kind of move in and out of the tensiometer. As the soil is drying out, it's going to pull more moisture out of the tensiometer, which is going to increase the suction pressure in the tube. And then vice versa, when you have an irrigation, the water is going to be moving back into the tube and it's going to reduce the suction pressure. So we have this mechanical gauge here that's outputting tension in centibars. And so that's when you can go out to the field, just take a look at your tension here and see how your moisture content is changing, and then convert that to volumetric water content and schedule irrigation accordingly. So the probes themselves are they're pretty inexpensive. I think that one, I was looking online, you can get that for about $50. So it's not a huge investment, and then the technology itself is going to mimic the suction pressure of plant roots, so that's a really great proxy for plant available water, so really nothing wrong with this technology. However, they are unreliable over a range of pressures, but without getting too far into that, if you're working with soils that have a really high moisture content, or else really coarse soils, this probably isn't the right instrument to be using to measure soil moisture. So there's going to be that time needed to convert those pressures into available water. So I guess also not ideal for that extra step. And then these require some maintenance. You do have to monitor them throughout the field season, because if that plastic cup at the top, if the water evaporates out of that, then you lose that suction pressure. So it is kind of something you have to go around and make sure that these are all primed and full of water. So the next probe that I wanted to show was the electrical resistance block. So these give the same output as a tensiometer, but they are an indirect measurement of soil suction, because you're actually measuring the electrical signal rather than suction itself. So this is made by Waterware. This is a Watermark brand sensor. This is what you buy from not the store, the online store, wherever you're going to get it. And so what we do is we create this PVC vessel. So you can see the granular matrix block is here, and then the lead wires are just strung through the PVC. Then we usually have a mark. You can put these in the soil. This one looks like, I will guess, a 1 foot, maybe an 18, maybe a 2 foot, I don't know. Anyway, we'll put them into the soil at this level, Then we have this PVC sticking up out of the soil. It's easy to find in the field, and then you just put a reader here. So we have this reader which applies the electrical signal, and then the tension is output here in centibars. So obviously as the water content goes down, the resistance is going to go up, and vice versa. In a moist soil, we're going to have a lower resistance because water is a great conductor of electricity. So these can be read manually with a reader such as this, or else they are suitable to set up to a data logging system, so that you can, I'm not super familiar with data loggers, but you can basically hook them up and then have that data logger feeding you the output every hour or something like that to reduce the need to go out to the field. And some of the pros, this is also pretty inexpensive. The probes themselves, I believe, are about $150 to construct, and then the reader itself is a few $100s. They're also very easy to install, and like I mentioned, suitable for data loggers. And one thing I did forget to mention, the cons of them, you do have to soak them in water for 24 hours before you put them in the soil, so there's just kind of some of the conditioning required, and if you do get a gypsum-based block, that will degrade in the soil over time. So I think those don't usually last for more than one field season. And the next set of probes that I wanted to show you are all based on this time domain reflectometry. So this TDR is a technique that measures the dielectric constant of soil, which is essentially the electrical conductivity. So the dielectric constants of different soil components is very different. Air and soil are very low, between 1 and 5. And then water is very high at 80. So really, when the probe's in the soil, any changes in conductivity are going to be attributed to changes in soil moisture due to these dielectric constants. And the dielectric constant has a positive relationship with volumetric water content, so as your moisture content goes up, your dielectric constant will as well. And obviously, back to soil texture, whether you're working with a clay or a sandy soil, they're going to have a different calibration curve to deal with. Okay, so these are the TDR probes. They obviously use that TDR technology. They consist of 2 or 3 metal rods that are connected to a signal or a power source, and soil moisture is measured by the time that it takes the electrical signal to travel down to the bottom of the rods and reflect back. So obviously in a more moist soil, that electrical signal is going to move a lot faster than in a dry soil. It will move slower. So these are a Sensiterra brand TDR probes, and we usually insert them in pairs at 2 different depths. So this one's a 6-inch, this one's a 12-inch, so that we can make sure we're hitting the shallower and deeper parts of the active rooting zone throughout the field season. These probes are also really nice. They have a wireless capability built into the top, so it's pretty straightforward. You just insert these into the soil. The data is transmitted to either a desktop or a cell phone application, and then we're getting fed the data output every hour and it's reported as volumetric water content. So there's not that need for all of those other conversions until you're going to calculate irrigation depth. So the pros of this is a really accurate technology, and it's easily upgraded for remote monitoring so that you don't have to make field visits to get your data. However, getting into this type of technology is a little more expensive. The probes themselves are going to be a few $100s. The transmitter that for the wireless capability is a few $1,000s, and then you're probably going to end up paying some yearly subscription fees. And there's a few cons, I guess, also with the installation. If these really require tight contact between the surrounding soil and the probe. So if you put these in without that good contact, it will give inaccurate readings. So not necessarily a con unless your probe is installed improperly. Okay, so the next probe I wanted to show was the capacitance probe. So this also uses the dielectric constants to measure soil moisture, but the probe actually creates an electric field, and then the dielectric constants are measured in that field, so it's called frequency domain reflectometry. So this probe is pretty much the same as the TDR probes, except you kind of just, you can see here, you screw it into the soil to a predetermined depth. The top part of this has to stick up above the canopy, so that, I think this is a solar panel that either transmits the data or charges the battery. But these probes are really nice because they have multi-sensors. So this one's got 2 or 3 sensors already built into it, so you don't have to put in more than one probe. So it's got pretty much the same pros and cons of the TDR probes. It can be expensive. It's a lot more expensive, I guess, than some of those other methods. It does require that proper installation to get good readings, and also it does have the multi-depth though, which is nice. So I wanted to show a quick TDR output example. So this graph shows volumetric water content on the vertical axis, and then time here on the horizontal axis. So in this example, if we're using a sandy loam soil, we've got a field capacity of 18% and a max allowable depletion of 13%. Initial soil moisture readings come in here at about 15% in that safe zone. Throughout the week, the crop's going to be using water. There's going to be hot and windy conditions, so the soil moisture is going to deplete until we hit that MAD at 13%. So that's when we calculate the irrigation depth required and schedule an irrigation. Here's a spike when we irrigate, bring that back up to field capacity, and then that, I guess, to simplify it, that just really repeats throughout the field season. We're just maintaining that soil moisture level and making sure, you know, the big things that are going to change that are going to be crop staging, whether it's in reproductive stage, and then those environmental conditions. If it's hot and dry, or if it's cool and wet, that's going to change our irrigation scheduling. So I just wanted to leave you with a few key messages about soil-based irrigation scheduling. The first thing is just that need to measure the soil moisture in a representative location in the field, especially if you're using only one probe or one collection point, which I'm thinking is probably the most realistic method, right? And it's also to make sure you're measuring soil moisture in that active rooting zone, because it is a moving target throughout the field season, so it's just making sure that you're accounting for that as you're scheduling depth. And there are several different methods and technologies that are available to measure soil moisture and inform these irrigation scheduling decisions. But there's pros and cons associated with each. So the most important thing is to identify a method that works best for an individual operation from that cost and comfort standpoint. There's this huge trade-off just between time and cost. You have those cheaper sensors that require you to go out to the field and measure everything manually, and then you can move to those more expensive probes that are outputting the data for you. You know, you get to an ag retailer that's going to actually give you a prescription. It's kind of where your operation fits in that whole, all of those options. And the overall goal is to schedule irrigation to avoid any delays in irrigation or unnecessary irrigations, because either way that's going to negatively impact your productivity, economics, and potentially environmental impact. So that's it. I'm happy to take any questions.